I am Jeanette Mumford. I'm currently at the University of Wisconsin. My training is in biostatistics. I got my PhD from the University of Michigan, where I worked with Tom Nichols, and my specialty was the analysis of fMRI data. And since then, I've worked in psychology departments. I worked with Russ Poldrak for a long time, and now, as I said, I'm at the University of Wisconsin. I work with Richie Davidson's group at the Center for Healthy Minds. Anyhow, that's who I am. I have a lot of tutorials online and other things, just FYI. But today, what I'm going to focus on is efficiency and design optimization for fMRI. And we'll see here that this idea is how to get the most bang for our buck. So what do you do if your sample size can't change? And a lot of the other tools that you're learning during this course will help with that. So pre-registering your study helps cut down on, sometimes I call it the garden of forking paths, all these decisions you have to make. So it helps you think those through ahead of time. So it cuts down on the multiplicity problem, and having your code publicly available and clearly written helps in many ways, but you also want to have a high-powered study. So the idea here isn't this is not something you can implement after you've collected the data. It's actually really important that you do this before you collect your data. And I would highly encourage you to do this before you even do your pilot study. And hopefully you are doing a pilot study. I can't imagine putting something in the scanner that hadn't already been shown to have a behavioral effect. So, what can we do before we collect our data to help guarantee that our power will be high in the future? And this is if we don't even have pilot data. So, if you had pilot data, you would just run a power analysis. But even if you don't have pilot data, you do this. But even if you did have pilot data and you ran a power analysis, I would still do this. If you ran the pilot study, hopefully you did it before you ran the pilot study. Anyhow, so let's think about the best way to increase power. So if I said to you, hey, what would you do to increase the power? If you thought about that for a second, hopefully you'd say, you know what, I would increase my sample size. And it's true, increasing the sample size is the quickest way to increase your power. But it's also the most expensive way to increase the power. But as I'm frequently reminded by people doing clinical work, often there's nothing you can do about your sample size. It's going to be small, either because accruing that sample is very difficult, or you're just limited in how much money you have for your study. Hopefully that will change over time. Hopefully we'll find ways to have bigger studies, because in a lot of ways that's kind of the only really great solution. But meanwhile, what do I tell you? Give up? Wait for things to change and you can have your N of 100? Of course not. You just do the best you can with what you have. So let's take a closer look at this variance. Of course, increasing the sample size decreases your variance. But we have other ways of lowering the variance, and that's what we're going to focus on. So before I show you the variance, I think it's just about the only equation in the whole talk. I first want to have you think about how we analyze the data, just in case you're not familiar with what this equation I'm about to show you is going to look like. So we analyze fMRI data in two stages. So the first stage is the within subject analysis. So this is when you're analyzing the time series data. And the second stage is the between subject analysis. So that's when you take the summaries from the first stage and you pull them together into a group model. You could be looking at a group average, you could be looking at linear relationships between bold, activation, and some age or some other variable like that between subjects. So each of these stages has associated with it a variance. Within subject variability or between subject variability. The within subject variability is from the first stage. We'll see there's two chunks to that variance. The between subject variance That's the one that basically goes down as we increase our sample size. So now for the equation. What does that variance look like? This MFX stands for mixed effects. So this is the mixed effects variance. This two-stage summary model that we use is the simplification of the mixed effects model. So you'll see there's three chunks here. I'm going to go through each of them separately. This is the first chunk, this CX transpose X inverse C transpose. Don't worry, I'm going to explain everything. And then there's two variances, sigma squared W and sigma squared B. Sigma squared B is the between subject variance. It's probably unknown. And so therefore, it's not going to do us much good prior to the study. The within subject variance also probably unknown. So that leaves us with this chunk here. And the good news here is we have 100% control over this before the study. We have no control over this after the study because the design's already been set in stone. But yeah, this has to do with the stimulus presentation, the ordering of the stimuli, and the timings between them. So if you've never seen one before, this is a design matrix from FSL. It's for a stop signal task, so there are go trials. This is time at 0 at the top and time's increasing as you go down. So every time this wiggles to the right, that's a go trial, and then it goes down. There's a bunch of go trials, it goes down, and so on and so forth. These are the stop trials separated into the successful stop trials and the failed stop trials. And then these two trials here, groupings of trials, are where the subject just kind of flaked out. So those are called junk, and they're just modeled, but they're not interesting. But we don't want that variability going into the residual. So that's the X, this part up here. The C, so that's this X. The C is the thing that tests our hypothesis. So in this case, I'm interested in successful stop larger than fail stop. So my contrast is 1, 0, 1, minus 1, 0. So this vector is C. So I'll show you how to make these in a little bit in R. So the efficiency equation then looks like this. It's the reciprocal of that thing I was just showing you. So if that little chunk of variance, if our goal is to make that really small, then that means the efficiency will be big. So goal, maximize efficiency. So the issue with efficiency, and even after I say this, when I've taught it in the past, I get a common question. It's just a relative measure. It allows you to rank designs so that you can pick the one with the highest efficiency. But there's no cutoff for efficiency, and that's what I'm still asked. I'll say that, but then it's really tempting that you get this number and you want to ask, well, wait, my efficiency is 10. Is that good? I don't know. 10 for you might be really good. 10 for somebody else might be really bad. It depends on what your task looks like. So all it is a way to rank one design better than another. So here's a motivating illustration. The goal here is to show you that yes, doing an efficiency calculation can in fact help the overall power, even though we're only focusing on that one tiny bit in that variance equation. So this example, I'm simulating a task with two stimuli, a positive and then a negative stimulus or images. The duration is they're on the screen for a second, then there's a 2-second fixation. So the fixation's fixed. Often with efficiency we jitter that, but we're leaving it at 2 seconds. The contrast of interest is positive minus negative, so we're interested in when positive is stronger than negative or larger. And the question I'm interested in is if I just shuffle the trial orderings, the positive and negative image orderings, how does that affect efficiency? And is that enough to have a substantial impact on the power? So the way this is going to work is I'm going to get estimates of those variances from real data. They weren't data from this task, but a different task, but I wanted to at least pick variances that were in the range of real data. So that's what I did. Okay, so how much can I increase efficiency by searching over random trial orders? So I randomly order the trials, created my design matrix X and computed that this efficiency. And I repeated that like 100 times for different orderings. And then I picked the best and the worst. And once I had those, I could compute power, in this case, because I had variance estimates. The within subject variance was 3036. These are arbitrary units. The between subject variance was 810. I fixed the sample size at 30 because, again, the exercise here is that we can't change our sample size. And the alpha, the cutoff for significance, is 0.05. So the plot I'm about to show you is taking that best and worst design from the efficiency study we did. What's power as a function of the effect size, which is the third unknown. So power is really hard to calculate. We don't know these variances usually, and we don't know the effect sizes unless we have pilot data. But I'm going to look at power over a range of effect sizes. And that's what we have here. Again, the sample size is fixed at 30. Power on the y-axis, effect size on the x-axis. That most efficient design is here in orange, and the least efficient design is in blue. So obviously the most efficient design always has more power than the least efficient design. That difference is smaller for really large effect sizes and really small effect sizes. But in the middle, so in this point here, the difference in power is about, it's almost 20%, it's 18%. 81% for that most efficient design versus 63%. So again, this is just a motivating illustration. This isn't the type of calculation you'll do. The type of calculation you'll do will allow you to rank the most efficient design from the least efficient. And the point of this is that it really can have a substantial impact in power. In this case, it's almost a 20% difference in power. Of course, you might be down here where it's only like a 5% difference in power, but again, we're trying to get the most we can out of our data. And if we do everything as cleanly as we can, hopefully that'll have a cumulative positive effect on power. What else can you do to increase your efficiency? Well, you could do the random trial order that I just did. I can't remember if I said this, but I did restrict it so that I would know it wouldn't be possible to have more than two faces or more than two houses in a row. So often you'll want to have those types of restrictions. You can also jitter your ITI by letting it be random. I'll show you code for using a uniform distribution, or a truncated exponential is more commonly used. What if you increase your ITI, or lengthen your stimuli, or increase the number of stimuli? So all these things will boost your efficiency. Or they can. They won't always be guaranteed to. So just another quick review of where these things come from, starting with X, the design matrix. Again, this is time from 0 at the top, time's increasing as you go down. This is how the stimuli are delivered. So there's a face first, and then a house, then a face, then a house, then a face, then two houses in a row, two faces in a row, so on and so forth. But these aren't what we model, because the stimulus time courses aren't what the things that we measure don't look like that, because we're measuring something that's filtered through hemodynamics. So what we have to do is we have to mimic that in our regressors by the operation of convolution with a double gamma hemodynamic response function. So that gives us this, and I will show you the code that you can use to generate these on your own in R shortly. So this time course that you see here is what I would expect to see in a voxel that was active to faces, and this is what I would expect to see in a voxel that was active for houses. So that is my X. And if my hypothesis, my alternative, was to find the voxels where faces is larger than houses, I would use the -1 contrast. So that is my C. So hopefully that's not brand new for you. And if it is, hopefully it makes sense. Last but not least, so efficiency allows you to rank designs, but if you have a bunch of junky designs, you're kind of picking the best of the worst. And it won't be a good design in the end. So this leads into this story where I was helping a graduate student who ran a successful behavioral study and was getting ready to put it in the scanner. And what we discovered was that if we were to follow the exact same stimulus presentation that was used in the behavioral study, there were different, basically a trial had about 5 different parts to it, but then there were different trial types. So it was like seeing a picture, and then they had to give a response, and then this other thing happened, and then 2 other things happened. And so the trials all had the same type of structure, but then there were different trial types, positive ones and negative ones, we'll say. But they weren't simple, like they saw a positive picture, they saw a negative picture. It had these components where the subject was giving responses and things like that. So what happened is if I tried reordering the positive and negative stimuli in random orders, I could find the most efficient design, but the collinearity was really bad, meaning the collinearity kills your variance. It's a huge problem in many ways. So it's best to make sure you're not in this realm of bad designs, and a way to do that is to check the variance inflation factor. The nice thing about this is it's not a relative measure. You just want it to be less than 5, at least less than 10, worst case scenario, but less than 5 is better. So I usually check this either for the first few randomly generated designs or when I'm all done to make sure I'm okay. Usually the first few, because I don't want to spend an hour running simulations on, junk. But I'll show you how to compute VIF as well. It's very quick. So let's look at the R code. Go to this link, and that will take you to an R markdown file where I have saved everything. So tinyurl.com Mumford-EFF. Take a little sip of tea while you do that. Okay. So that should take you here to my GitHub repository for the course. If you click this here, so what this is it's an R markdown file. And so it has some text where I'm kind of explaining the things that I'm saying right now to you. And then it has R code. If you want just the R code part with the R comments, I tried to comment heavily. Go to that link that I just clicked, which is here. Yeah. So first, you need to know how to make a single regressor. I'm going to use this NeuroSim library. If you've never installed it before, you need to use this install.packages command. You only need to install a package once until you update R. The thing you need to do every session where you're using it is this library command, which loads that so that you can use the functions, access the functions. So that'll give these little output lines. And it's beta software, so let them know if you find bugs. And here's how you make a single regressor. So the first thing you do is you specify the run length. I wonder if I can make this font bigger. Oh, yeah. Okay. I have horrendous eyesight. So, okay. The first thing is the run length. I set it to 60 seconds. So this could be a little bug in the problem, but it's really easy to sidestep it. Make sure your run length is a multiple of the TR. In this case, my TR is 1 second, so it's fine. But if my TR was 2 and run length was 61, I'll get an error message later when I'm using the function from NeuroSim. And honestly, for your efficiency calculations, you can just set the TR to 1, even if that won't be the TR of your future data. It should be fine. I only have 3 trials in this little quick example. A trial that starts at 10 seconds, 20 seconds, and 30 seconds. Each trial is only a second long. And then there's this effect size thing that you have to set. So as the name of the package suggests, NeuroSim, this is used for simulating bold fMRI data. Here we're just using it to create a design matrix. So in a simulation, we would have bold effects. And we don't want to scale our regressors at all. So just set f.size to 1 and always leave it at 1 for this. Then we create the regressor using the specified design function, and you just feed in the things that we just specified up here. ons.times, dir, run.length, tr, f.size, and then this does the convolution. If you leave this out, you'll just get a boxcar regressor. So you'll want to set this to the double gamma HRF. If you haven't used R before, one thing that's different is the period is not special. Like if you use MATLAB before, that's how you create a MATLAB structure, and that's not what this is. Yeah, I got out of the habit of using an underscore because I follow the Google guidelines for writing code or something like that, just to kind of unify my code, and that's what I use. Okay, then I plot the regressor, and there it is. So you can see the trial at 10 seconds, as I said, there's this blurring and delay, and so it doesn't peak until about 16 seconds. So that's what the convolution does. And so this would be the expected time course that we would see for this fictitious task. Okay, and I have little things on your own. You can try changing things. But always keep that effect size at 1. You're not going to be using that for efficiency. The next section, as it says, it recreates that example I showed in the slides, at least the efficiency calculation part for the 2 stimulus thing. Here I'm using faces and houses. I realize now that in the slides I use positive and negative, but it doesn't matter. It's just 2 stimuli. And first I'm going to start by just showing you how you would create the design matrix, and then we'll do the actual efficiency calculation after. So I'm going to have 2 stimuli, 30 of each, so n trials each is keeping track of that. And as I said before, I want to restrict this because statistically the most efficient design is going to have all the faces followed by all the houses, which is psychologically super duper boring. So in order to balance what's statistically best and what's psychologically best, I have a restriction that there can be at most 2 of the same stimulus type in a row. So this while loop does that. So if I was just to use this line right here, what this is doing is this rep is repeating 31s and then 32s, that's what each does. And then sample is randomly ordering them. So this is creating that random order. But now I need to check if that random order has more than 2 1s in a row or more than 2 2s in a row. This RLE function, if you pull out the lengths information from it, what this does is it breaks the sequence into lengths and values. So if you had 5 2s followed by 3 7s, it would output a 2 and a 7 in one vector and then a 5 and a 3. So the 5 and the 3 are these lengths. So how many repeats were there? So we basically need to make sure that the length of the repeats is never beyond 2 or 3 or larger. So that's what I'm checking here. So if this is true, keep looking is 1. So if keep looking is true, it's going to keep going. R reads a true as a 1. Right, so this won't take long to run with 30 of each trial. And then the rest is setting up the duration, 1 second duration, ITI is 2 seconds. So I'm creating a vector with all the trials in it, and I'm going to subset my faces and houses when I create the separate regressors later. Now, to create the onsets, the first trial I'm going to assume starts at 0 seconds, which would mean the second trial would start at the first dir plus the first ITI. So the first trial has to happen, first 1 second, and then the first ITI. So the next one would be at 3 seconds. And then it's 3 seconds after that. So to get the onset time, the first one's going to be at 0. And then I'm going to use this cumulative sum function here to get the onset times for the rest of the stimuli. The only problem is we get an extra because, as I said, if you take here the duration plus the ITI, that gives you where the next trial needs to be, how far you need to move before the next trial. But the last DUR and ITI, nothing's actually happening after the very last trial. It's the end of the task. So I'm going to trim that last one off because it's referring to a trial that doesn't exist. So that's what this is doing. That's what this is doing, the second line here. It's going from the first to just up to, in this case, 60, and dumping that 60 first. Then the run length, I add 9 seconds. Again, make sure your run length's divisible by the TR. My TR is 1 in this case, so I don't have to worry. Effect size is 1 again. Then I create the faces regressor by subsetting here the trial type equal to 1. Those are my faces, and then I do the same for duration. Change it to 2 for the houses, and then I can plot it. And there we go, faces and houses regressors. Okay, to calculate efficiency, all I need to do is put these into a matrix, which is what I'm doing here. Now I'm actually calculating efficiency. So my design matrix has to also include a column of ones. I didn't show that earlier, but you do need to include that. So that's what this rep function is doing. And then I add my faces regressor and houses. cbind is column binding those different columns into a matrix. So this will be however many TRs it was by 3 matrix. And last but not least, my contrast is 0, 1, minus 1. So faces minus houses. The solve function is how you invert a matrix in R. And then the multiplication, it's annoying. You have to use 3 keystrokes. It's percent multiplication sign percent for matrices. So efficiency then looks like this. 1 divided by, the contrast was, it wasn't a row vector, it was a column vector. So the transpose goes here. So transpose of the contrast, multiply it by the inverse of design matrix transpose times itself, and then multiply by the contrast, and I get an efficiency of 13. And again, it's tempting to be like, oh, I got 13, is that good? I don't know. Generate another design, and I can tell you which one's better by comparing the efficiencies. It's only a relative measure. Okay, so that's what we're going to do here. I only did 10 so that this wouldn't take forever to generate. In real life, I would do 5 to 10,000, however many you can sit there and wait for your computer to do. So here I just do 10, and basically all I'm doing is I'm taking all the code from above and putting it into a for loop. So the for loop's going to loop through 10 times. These are the things that don't change. The number of trials doesn't change. The durations don't change. The ITIs in this case don't change. And the onset times don't even change. And we're changing the order of the stimuli. Run length's the same, TR is 1, effect size is 1. I'd like to save the efficiency values and the design matrices. What I'm creating empty arrays here for those things. In a real, this is just to illustrate what the most efficient and least efficient designs look like. You would also generally want to save the trial orderings and the onset times, the information you need to actually program your task. All right, let's get to the loop. First is that while loop. So the for loop starts here. So it's going to go from 1 to 10. This first chunk is what we saw before to make sure we don't have more than 2 faces or 2 houses in a row. Then I make my design matrix and my contrast as I did above and calculate the efficiency and save the design matrix. So all this is just repeating the code above. So I let that run, and then this next chunk plots the best versus the worst. So what you'll see is, as I said, blocky designs, having blocks of trials, are more efficient. And in the higher efficiency design, wherever the time series goes up higher, that means you had two, in this case was this faces in a row and two houses in a row. And this is just face, house, face, face, house, face, alternating. So the higher efficiency has more doubles in a row. Face, face, house, house, face, face, house, house. Whereas the lower efficiency tends to alternate between the two. So, again, that's the statistical versus psychological trade-offs in the different designs. So you'll want to build that into your efficiency calculation. And that's kind of why I'm a fan of writing this code myself. And I should have said that sooner. There are a couple of tools that I'll lead you to later that are really easy to use, but they're limited in what you can do with them. So since the people I work for tend to have more complicated tasks like that, graduate student's task was super complicated. I had to have these 5 things that were always in a row. And then when I shuffled things, those 5 things had to get shuffled together, which is kind of hard to program into a GUI type tool or a web-based tool. But those tools are still really helpful for some of the more simple designs. So I always code it myself. The first time you do it, it takes a little bit of time, but then after that, tweaking your code is a lot easier. So take my word for it. So let's see. Now you know how to do the efficiency calculation. Of course, you still want to check the variance inflation factor to make sure you didn't find the best of the worst. It's just one line of code. You omit the intercept when you do this. You take the correlation between the regressors, you take that correlation matrix, and you invert it, and then look at the diagonal. And you get 3.62. They're the same, and that'll happen if you only have 2 regressors. They'll have the same VIFs. But less than 5, so we're happy. This is good. So again, VIF is not a replacement for efficiency because VIF is just looking at one regressor at a time, whereas efficiency is getting at the contrast that we're actually interested in. So slightly different things. On your own, I have some recommendations here. One thing is to try jittering your ITI. So this runif function can be used to generate uniform random samples from a continuous uniform. So this will randomly generate a vector of 60 numbers that range between 2 and 4. You can also use a truncated exponential. Oh, this did not format right. This is supposed to be a lambda symbol. Sorry, my cat is chirping. She never makes noise, but she is right now. Okay, so truncated exponential. Typically when people do this, and this is fine, you choose a parameter for your exponential distribution. It has one parameter. And then you simply truncate it. You don't count values that go greater than, in this case, 3 seconds. And that's fine. I like to do it more in a more controlled way, I guess. I like to be able to, for example, estimate the theoretical mean and things like that. So this code will allow you to do that. And you don't have to throw anything away. It'll just give you truncated exponential samples. Okay, so you put the lambda for your exponential distribution. You put the truncation, so this will limit between 0 and 4 seconds. 40 samples, and then I'm going to shift it because typically people, if I tell people like, oh, your ITI or your fixation might only be a half a second long, they're like, oh, that's not going to work for me. You're going to have to make it longer. So that's what the shift value does. It shifts this range from 0 to 4 to 2 to 6, basically. It shifts everything up to. This is the unshifted truncated exponential's theoretical mean. And these next 2 lines are creating the samples from the truncated exponential distribution. And here is the theoretical mean. It's 3.2 in this case. So you can, if you want a mean of a certain value, you can tinker with that a little bit. And as you see, the values do range between 2 and 5.84, or 6, 2 and 6. If I hadn't added that 2 was my shift value, that means I would have had an trial interval of 0.002 seconds, so 2 milliseconds. That would have not been good. Okay, so that's why you shift it. There are a couple of tools I have links to here, OpSeek and NeuroPower Tools. OpSeek is a command line tool. NeuroPower Tools is a web-based tool. So you can look at those if you want to know more. I also have quite a few videos that go into more depth about this. There are different types of efficiency. I didn't have time to talk about them here. So this link will take you to that playlist on my YouTube channel. So in summary, you have to do this efficiency study. Even if you have 100 subjects, you're still going to want to get the most bang out of your buck. So the efficiency study will make sure you have the best design you can have, but don't forget to also look at the variance inflation factor to make sure it's not the best of the worst. You want it to be the best of the best. So yeah, it's a nice way to check how bad the collinearity is. That's it. Thanks for listening. Hope you're enjoying the course. If you have questions, I know there are various ways to ask questions for the course. And another way on top of what you've been told is you can post them to my Facebook group, which is just Mumford Brain Stats. So it's great. So yeah, enjoy the rest of the course, and thanks again.